is cyclically quasi-monotone, means when you have P1, Pk, price vectors, and xy in the corresponding demand set, then the minimum over I from 1 to k of Pi xi minus xi plus 1 is less than or equal to 0 after defining xk plus 1 equal to x1. This is a definition. But now we are going to prove very easily that if the utility function has no local maximum, then the corresponding demand correspondence is cyclically quasi-monotone. You have to interpret this condition appropriately. This means that this implication holds true, so that for every finite sequence of prices and corresponding commodity bundles, then you have that condition, okay? For every finite sequence of whatever length k, for k from 2 to infinity. Okay. Let us prove it. And we'll do it by contradiction. So suppose x is not cyclically quasi-monotone. Then you can find a finite sequence of p's and corresponding commodity bundles such that this minimum is not less than or equal to 0. This means the minimum of Pi xi minus xi plus 1 is strictly positive. And the minimum being strictly positive means that each individual term in this minimum is strictly positive. And of course, this means that Pi xi is strictly greater than Pi xi plus 1. And now I claim that Pi xi is equal to 1 in the situation we have. Do you agree? Do you see any reason why Pi xi should be exactly equal to 1, we only have one assumption, that U has no local maximum. It must be a consequence of this assumption. And it is. Because what is Xi? Xi is an optimal solution to the maximization problem Pix subject to U of x subject to Pix less than or equal to 1. Xi is optimal. If at the optimal point we had a strict inequality, if we had Pixi strictly less than 1, then we would have a local maximum, because this open half space defines an open set. Well, open relative to our space, R plus n. We are in R plus n, okay? So we are considering openness in the non-negative orthont. We cannot have a maximum, a local maximum, cannot have a maximum on an open set. This is a local maximum. Do you agree? Well, and then that's it. Because this says that Xi plus 1 satisfies the budget constraint corresponding to Pi strictly. Then it cannot be optimal for Pi, as we have just seen. Every optimal solution, Xi for instance, satisfies the constraint with equality. Xi plus 1 satisfies the constraint. This is less than 1, but not with equality. So it cannot be optimal. So it's strictly worse than the optimal one. Means that the objective function assigns to Xi plus 1 a value strictly less than the value at the optimal solution, which is Xi. And do you think it is possible? For I equal to 1 to k? Not, because 8k plus 1 is equal to x1. Okay? So we have u of x1 greater than u of x2, u of x2 greater than u of x3, and so on and so forth, until we arrive at u of xk, which is strictly less than u of xk plus 1. But xk plus 1 is x1. So we have a cycle of strict inequalities, which is impossible. You see, a very simple condition, which is quite realistic, that there is no local maximum. For instance, this happens if u is strictly increasing. You increase x, and u of x strictly increases. This means this cannot be optimal, because you can increase, still satisfying the budget constraint, and u would increase. So there is no local maximum. Okay? So this is a simple situation. So let's say cyclic quasi-monotonicity, very easy to obtain. But non-monotonicity. Let us see as the examples. Well, I'm lazy to look for the expression we found for the Cobb Douglas functions, and I don't remember. But believe me that for the Cobb Douglas function, if you increase the price of one good and keep the other prices equal, then the demand for that good will decrease. Look at the expression. If you want, I can look for the expression. For Leontief, I can do it because I remember, it's very easy. The optimal, the demand under price is P was 1 over PA times A. So if one PI increases and the other prices become the same, this increases, then Xi of P decreases. Not only Xi of P, everything else decreases. Okay? If your utility function is Leontief, and tomorrow the price of just one of the ingredients increases, you will buy less of that ingredient, but also of every other ingredient, because you only care on the proportion. So you would not keep buying, let's say, the same as yesterday, because then there will be too much, because the one which you are forced to buy less makes a restriction on the amount of the food you can produce. This, agreeing with your intuition that a decent demand should be monotone. But it's not the case, and I was meditating, how do you have this strong faith on monotonicity of demand? And then I reach a conclusion. You are a millionaire. Okay, that's the only possibility. You don't care about money. If you are not a millionaire, I will give you a very easy example. I will give you two examples, which are essentially the same, but one without mathematics, and the other with mathematics. I prefer the other because I invented the utility function. So one, how much money you spend every day in food? I don't know, suppose 500 rupees or 1 rupee. Doesn't matter. You cannot afford 1 rupee more. Okay? Then, there are two goods available. In economics textbooks, those goods are classically potatoes, and they refer to island, potatoes and meat. But this is not a nice example to give here, because many Indians are vegetarian. And by the way, I love the vegetarian Indian food. So let's replace meat with, I don't know what, mango. Okay? A very delicious fruit. Then your food reduces to potatoes and mango. You like mango. Potatoes, well, you can eat, but you don't get any pleasure out of eating potatoes. So if you are not a millionaire, as you are, then you would eat only mango. Okay? But mango is too expensive. It's more expensive than potatoes, I suppose. Is it? So you cannot live just on mango. You have to eat some potatoes too. So you spend your money on mango as much as possible, and then potatoes until you spend your rupee. Tomorrow, potatoes have increased their price. The price of the mango is, so potato is now more expensive, but still cheaper than mango. You cannot continue with the same regime of yesterday, because then you would exceed your budget constraint. So you have to change. And there are only two possibilities. Either you eat more mango and less potatoes, or more potatoes and less mango. Do you think you can eat more potatoes and less mango, more mango and less potatoes? No, because mango is still more expensive. So you are forced to eat less mango and more potatoes. Are you now convinced? Of course, because the budget constraint plays a role. If there is no budget constraint, no. So this is well known to economists and very easy. as since I think 1895 at least, in which Alfred Marshall is was a big name in economic theory. In his in one of his books, wrote not these examples with potatoes and meat, but after having observed how people travel in those times in Holland, in the Netherlands, he said to make long trips, you have two possibilities in those times, by train or by boat. Train is faster, but boat is cheaper. So they combine part of the trip by boat, part of the trip by train, trying to go by train as much of the trip as possible. But then he observed that when the prices of boat tickets increased, people was using the boats for longer trajects. It's the same. Now I'll give you, but of course, this depends on your preferences. In the case of potato, and if your preferences are not to starve, then you have to behave as I have mentioned. But in particular, this means that your preferences are not Cobb Douglas or are not Leontiev. They are different. Can you produce a reasonable utility function showing this phenomenon? By the way, let me introduce some little terminology. Goods like potatoes in this example are called inferior goods. Mango would be a normal good. They are also called given goods. Because Giffen was another economist of those times studying this phenomenon. Okay? So, but then, as I said, this depends on your preferences. If your preferences are Cobb Douglas, you have monotonicity. If your preferences are Leontiev, you have monotonicity. But if your preferences are, as in the potato mango example, then you don't have monotonicity. The law of demand does not hold. Now I was thinking, okay, that's very nice, but I want to construct a simple and reasonable utility function for which is not monotone. And I invented the following one, which has no, this is not the good one. Okay. This lack of monotonicity didn't happen in producer theory, because in producer theory there were no budget constraints. They were minimizing the cost, but they simply, okay, I will apply, the firm says I will apply for a loan if I need more money than I have. So there is no budget constraint. Well, the example is the following. Potato mango. I suppose there are, but I don't know. I have never seen another example. But I will give you several results showing that sufficient conditions for monotonicity and for necessary conditions for monotonicity, which are actually necessary and sufficient. I will give you one, which is mine, but still unpublished. Well, I published it in a book chapter, which was a survey paper, but without proof. So the research paper in which all this should be based is waiting since, I think this chapter was published in 2005. So it's waiting for 25 years to be written. All the proofs are there. I just need time. In the meantime, I have written many papers, other papers for many other reasons, but this one is in the queue. One of the reasons is that my co-author for that paper is not pushy. So I give preference to the others who are. Okay. In fact, I am committed to write 2 joint papers with him. This one, but waiting since 2007, is a famous economist, John Kua. He's originally from Singapore, obtained his PhD in Berkeley. At the time we started to collaborate in 2000, he was in Oxford. And I think he's, however, somewhere in the US, but I don't remember where he went. I can search the web. John Kua. There are 2 Kuas, economists, both quite good. This one is John K.H., and the other top economist is, I think, David. I never met him. D is the initial. So the question is, should you be able to produce a utility function describing potato mango example? Well, this one I have invented more or less than this. So there are these 2 goods, and u of x1, x2 is x1 plus x2 minus 1 if x1 plus x2 is less than 1, and x1 if x1 plus x2 is greater than or equal to 1. Let us examine this utility function, my utility function, from a mathematical point of view and from an economics point of view. Mathematically, u is nice, u is non-decreasing. If you compare 2 points here, it's clear that if x1, x2 increases, then this increases. If you compare 2 points here, it's clear, the same it's clear too, because you only care of x1. Well, if x1 remains the same and x2 increases, it takes the same value, okay? But anyway, it exhibits this non-decreasing behavior. If you are moving from this zone to that zone, then you are moving for a zone in which utility is negative to a zone in which utility is positive. So you are improving. U is increasing. And if x1, x2 is taking higher values, you can only be moving from here to here, not in the opposite direction. Because x1 plus x2 increases if x1 and x2 increase. Okay, so do you agree that this utility function is non-decreasing? but it's also quasi-concave. Sorry, it is not continuous, as you see, but it is upper semi-continuous. So what are its upper level sets? We will see that they are convex and closed. This is the meaning of quasi-concavity and upper semi-continuity. Fixed and negative level. Or first, easier first a positive, a level alpha greater than or equal to 0. Then u of x1, x2 greater than or equal to alpha, if alpha is greater than or equal to 0, then means you are in this zone because utility is negative. So this inequality means two things. x1 plus x2 greater than or equal to 1, you are in this zone. And then the utility is greater than or equal to alpha, because that's the utility for such point. And this defines a closed convex set. Okay? Now, if alpha is negative, then u of x1, x2 greater than or equal to alpha, then you may be in this zone or in that zone. So this means that either you are in the first zone and in this case this is the value which is greater than or equal to alpha. Okay? And or x1 plus x2 is greater than or equal to 1, in which case the utility is non-negative, so it's automatically greater than or equal to alpha. But this condition implies this one. No, the other way around. This condition implies this one because this is greater than or equal to 1 plus alpha, and alpha is negative. So in this case, this condition of belonging to the upper level set simply means x1 plus x2 is it okay? No. This is the upper level set in this case. Let us see. If we are in this level set, then either we have plus alpha. Either we have this, or we have that. But then we also have this, because 1 is larger than 1 plus alpha. Conversely, if x1 plus x2 satisfies this inequality, we have to see that x1 and x2 is in the upper level set. There are two cases. It may be x1 plus x2 less than 1 or x1 plus x2 greater than or equal to 1. But, so, in the first case, if this less than 1, every pair satisfying this condition satisfies it. Okay. In the second case, also, but I think this is, I'm explaining this in a very unclear way. So let me say it again. So suppose x1 plus x2 is greater than or equal to 1 plus alpha. Two cases. As x1 plus x2 is less than 1. Good. And the second case is x1 plus x2. I mean, if x1 plus x2 is less than 1, this is automatically satisfied. Because, no, it's the opposite direction. If this, okay, wait a minute. If x1 plus x2 is here, then it also satisfies this condition because alpha is negative. So the conclusion is that in any case, u of x1, x2 I think my third attempt will be convincing. U of x1, x2 is greater than or equal to alpha. If this condition is, let's proceed in an ordered way. So if x1 plus x2 is less than 1, then u of x1, x2 is this. And then because we are assuming this difference, which is u, is greater than or equal to alpha. If x1 plus x2 is greater than or equal to 1, then we have to prove, in that case, this is x1. So we have to prove that this is greater than or equal to alpha. I think it's better if we make a picture. So let's x1, x2 equal 1 be this line. Okay? Then, being in the upper level set when alpha is negative means that either we are in this line, but above this line, x1 plus x2 greater than or equal to 1 plus alpha. So this is x1 plus x2 equals 1, and this is x1 plus x2 equals 1 minus alpha. We may be here, or maybe above this line. We are always in the non-negative orthant, but with x1 greater than or equal to alpha, which is automatic because alpha is negative and x1 is non-negative. So we are making the union of this with the half plane x1 greater than or equal to 0, which gives this set, which is certainly a convex polyhedron, unbounded convex polyhedron. Okay, it's easier with a picture, but I mean, if you are careful, you can do it without the picture too. The point is that in this case, this imposes nothing. That's the fact. Because x1 is non-negative, this is what I didn't take into account in my previous explanation. Is this clear, or should I try for once again to make the reasoning? We are having troubles only when alpha is negative. Yes. So this condition doesn't impose anything on x1, x2 in that case. When we are in the case x1 plus x2 is strictly less than 1, then in this case, this condition means u of x1, x2 means x1 plus x2 minus 1 greater than or equal to alpha. So either this or that. But in this case, u of x1 greater than or equal to alpha is satisfied for every x1, x2. So we are left with this condition alone, as we have seen in the picture. Okay? So we get a closed convex set, actually a closed convex unbounded polyhedron. What is important is that it is convex and closed for every alpha, and this means that the function is quasi-concave and upper semi-continuous. Very acceptable utility function. If we compute the indirect utility function, then we would be able to recover this by our formula from the indirect utility function. Is clear? So, mathematically it is acceptable. Do you agree? And what about from the economics point of view? This is more or less what I told you about potatoes and mango. X1 is mango. And X2 is potatoes. And my doctor told me that I have to eat 1 kilo of whatever food. Only 2 foods are available, potatoes and mango, to stay healthy. But I only like mango. If the total amount of what I eat is too little, is less than 1 kilo, I don't feel well. So I get a negative utility, which is equal to my eating deficit. And since I don't feel well, I am even unable to distinguish between potatoes and mango. Yeah. So this is why in this case, my utility does not distinguish. There is symmetry between x1 and x2. Okay? But as long as I am eating enough, I am enjoying mango. My utility is the amount of mango that I am eating. This doesn't mean that potatoes are useless to me. Potatoes allow me to be in this zone rather than in that one. Okay, but this reflects reasonable preferences. So when I am eating very little, I prefer to eat more than eating less. When I am eating enough, I prefer to eat more mango than eating less. And I prefer to eat more than to eat less. I mean, I prefer to be in this zone to be in that one, because here I have positive utility, not negative, and here I have negative utility. So is the utility function I invented acceptable from an economics point of view too? Do you accept it? mathematically and economically, or you have any objection? It was also new to me. I invented it. So I'm not surprised. But you don't accept new things? I was surprised too. But I cannot, I don't mean be. I cannot give you an easier example with a clear economic interpretation. So this function, I think, I like it very much. It's my function. So don't criticize it, please. I mean, it's mathematically very good. This you cannot deny. And economically, it has this interpretation. I insist. If I'm not eating enough, I feel so bad that I only care of how much, what is my eating deficit. And this is the eating deficit. And in that situation, when I feel so bad, potatoes and mangoes for me are the same. I cannot distinguish between them. Now, if I am eating enough, then my utility, X2, potatoes play a role because they allow me to be here rather than there. But the actual utility I derive is from the amount of mango I'm eating. This what? I don't know. You can try. No. It must be like this, I think. But okay, no, I'm not just saying, just look, I have found a function that can be interpreted to express the potato mango example. But let us see that with this example, it is the case that when the price of potato increases, under a particular situation I will mention, then the demand for mango, for potato increases. You can produce, if you want, differentiable utility functions satisfying this, but I don't have an economic interpretation for them. So suppose the situation is as I described. Potatoes are cheap, mango is expensive. This means, so first we are solving the maximization problem, u of x1, x2, where u is that function that you don't like, subject to p1 x1 plus p2 x2 less than or equal to 1. And assume that P1, the price of mango, is too high. It's greater than 1. So the 1 kilo I need to eat every day cannot be of mango, because then I would be spending P1, which is too much. I have only 1 rupee to spend. And suppose that potatoes are cheap enough. Of course, prices are not negative, but less than 1. So, I mean, if I am desperate, I just buy 1 kilo potatoes and I am healthy. But I don't buy 1 kilo potatoes, okay? But if I buy 1 kilo potatoes, then I spend P2, correct. It's less than 1. Okay? So let us examine this particular situation. And let us try to solve the optimization problem in this particular case, graphically. So this is the line that separates these two zones. We want to be on the right of that line because it's where the utility is non-negative. But now let's represent the constraint. This is a half plane. How should I represent its boundary? Since P1 is greater than 1, 1 over P1 is less than 1. Somewhere here. If, since P2 is smaller than 1, 1 over P2 is greater than 1, so is somewhere here. So this one is the line P1x1 plus P2x2 equals 0, equal 1, sorry. Okay? It takes the value 1 at the points 1 over P1, 0, and 0, 1 over P2. That's the line. And we have to be below this line. Okay? So the feasible set, this is the feasible set. Okay. This inequality, the feasible set. And over this feasible set, we want to maximize our utility function. We want to be here, on this little triangle, because on the rest of the feasible set, we are below this line where utility is negative. So only this little triangle in the feasible set has points with non-negative utility. And we maximize there. This means maximizing x1, which is the point with the largest x1, the intersection point. Okay? So this is the x1 component of this point is the demand for mango. And the x2 component of this point is the demand for potatoes. Now, tomorrow, P2 will increase. Potatoes become more expensive, but still not as expensive as mango. And mango keeps its price. So because 1 of P over P2, since P2 has increased, 1 over P2 decreased. And then what happens with this line? The picture is too bad to see, but you can represent it in your mind. What would happen, how would this intersection point would change if you keep this point here, but 1 over P2 goes a little bit below. What will happen with the intersection point? How will it move? How will it become? The intersection point is always on this line. It will come higher. No, it will come higher. So you have, let me exaggerate the picture. This point is coming down. And then we are joining it with 1 over P1. The picture is terrible, but good enough to tell me that the point is now higher. And its height is the demand for potatoes. But if this graphical argument does not convince you, I'm not surprised because the picture is horrible, but then find the intersection point, solving a very simple system of linear equations. Okay, so you have to solve the equation x1 plus x2 equal 1, p1 x1 plus p2 x2 equal 1. And the solution is x1 equal to 1 minus p2, p1 minus p2, and x2 equal to p1 minus 1 by 1 minus p2. Solve the system. This is the solution, or check that it is the solution. Then we are interested in x2, which is the demand for potatoes. How does it depend on the price of potatoes in this particular situation? The price of potatoes appears only here. So if it increases, but still is below P1, so this decreases, but this is in the denominator. Denominator is positive because mango is expensive. P1 is greater than 1. Okay, so x2 depends in an increasing way on P2. So P2 increased, x2 increased. Potatoes are more expensive, you buy more potatoes. Okay? So I hope I have succeeded to convince you that the law of demand is not always satisfied, not in artificial situations. Okay? Now, there is a way for but this depends on the utility functions. I mean, it was not easy to me to invent this utility function. I had to think. And if you have Cobb Douglas, no problem, monotone. If you have Leontiev, no problem, monotone. So it depends on your preferences. In this case, your preference is not to starve. Quite reasonable preferences. Then, but now the point is, for which utility functions does the law of demand hold? So for which utility functions the corresponding demand mapping is monotone in our sense. The classical result, I will tell you some other day is the so-called Mityushin-Polterovich conditions. Mityushin-Polterovich were or are two Russian economists or mathematicians or mathematical economists who published this result in Russian, but there are translations into English, in 1978. I'm not going to mention this result now, but I will tell you. But this is, in my opinion, quite unsatisfactory for the reasons I will tell you when I show you the result. Okay? In particular, it uses that the utility function is concave. This is meaningless. Quasi-concavity is meaningful for a utility function, but concavity, no. But I will comment more about this. And that it is of class C2. Well, and other assumptions, which I don't like very much, and also that they are sufficient but not necessary and sufficient. In the book by Mascolell, Winston, and Green, Microeconomic Theory, 1995, these conditions are stated as an exercise. Probably the students of economics are very clever and can solve such difficult exercise. I can't. Okay, but yeah, I remember now where I found the translation. No, it was not a translation. It was probably a new proof of those conditions in an appendix of one book by Hildenbrand. I found a clear proof, and then I was able to, I wouldn't be able to produce such a proof, but I was able to modify that proof to make the condition necessary and sufficient. Still unpublished. But still, C2, what about removing C2? Because it happens like, it's a similar situation as I told you when we discussed about Weierstrass theorem. I said, look, on one hand, you have topology. On the other hand, you have just a global minimum. There is no topology in the conclusion. What does it mean? That the topology is not essential, it's just a tool. So then you are free to use the topology. Similarly, it happens here. In the conclusion that the demand is monotone, it's just an algebraic condition. Do you see any differentiability in the demand, in the definition of the demands correspondent, the demand function? No. Then we should be able to, theoretically at least, to find algebraic necessary and sufficient conditions for monotonicity, not involving any differentiability at all. I was trying for a while, but I didn't succeed. Maybe it's time to stop, but before stopping, just I give you the statement I will prove at the beginning of the first class. And let's make a few comments about that statement. This is, when I was interested in this problem, some 25 years ago, 99, 2000, I made some search in the literature and I found an unpublished paper by a French economist, which was not about this topic, but he needed for some conclusions about econometrics, I don't remember what, he needed to consider monotonicity of demand. The name of this French economist, I never met him, is or was Millerand. Then I found a statement which I liked. I looked at the proof, I looked at the assumptions, and I think the assumptions can be weakened and the proof can be simplified. But it was his idea. Again, I am unable to produce what he produced, but I am able to refine what he did. Okay? His result, you'll tell me if you like it or not. There are reasons for liking it and reasons for disliking it. Suppose U is concave, and has no maximum. Okay? Has no maximum. I don't need to specify if I mean local maximum or global maximum because such a distinction does not exist for concave functions. So U concave has no maximum and V convex. The indirect utility function happens to be convex. Then X is monotone. Do you like this statement or you don't? Reason for liking it, it's very clean. Concave, concave, well, no maximum. Easy to remember. Reasons for disliking it. Economically, it makes no sense because, as I said, I was criticizing using Polterovich because assuming that the utility function is concave, and I am now assuming that not only that U is concave, but also that V is convex, which is an artificial condition, as artificial as saying that U is concave. Well, okay, this is a result, and this will inspire us a lot of things, which I will tell you. And everything I am telling you, starting with this, well, this you can find more or less in Millerand with unnecessarily stronger assumptions. Maybe he was using strict concavity or strict convexity, and the proof was a little bit more unclear than the one I will present. But everything derived from this observation is mine and is unpublished, except maybe without proof in a chapter in the Handbook of Convexity and Monotonicity. Try to prove it. I stop here following my technique of interrupting at a very exciting moment, because I'll tell you that this proof is just a couple of lines. Try to do it. Okay? I will do it tomorrow at 10. These conditions are weaker than the ones used by Millerand, in which he was using maybe strict quasi-concavity here or strict convexity here and something else which was unnecessary. So I weakened the assumptions and simplified his proof a little bit. But it's simply his idea, it's essentially his idea. Okay? This is unpublished. I think it's from 1974. I mean, very old, so if after 50 years he has now published, I don't expect this paper to appear. I also forgot the title, but I may have a copy, hard copy at home. Okay? Okay. So we stop here.